sound a little bit like I do. My internet's not too good, but should be. Can you see that?
I don't see it. Can someone confirm, please?
I can see it, Oliver.
Yeah. Cursor highlighting me. That's all you need.
Yeah,
Yeah.
that seems to work.
Yeah, I see that fine.
Thanks.
Okay. So I think I think we can start. So it's so. Yeah. So say a few words. So Oliver is working at UCL, and you have a lot of experience in. You have 17 labs for a few months, I think so, and you will share your experience with real-time reconstruction in Matlab. You can go ahead.
Thank you, Valerie. So as I was just saying to Valerie, I think it's fine if you have a question that you're burning to ask while I'm talking, please just butt in and start talking. I'm running over anyway into the Q&A session. So if there are too many questions, I'll just say that we'll just leave them until the end. But I quite like having interruptions and also from the other speakers. Thanks very much to the others for great talks, and I've learnt a lot. So this is all in the README file on the Gadgetron Online Class GitHub page, and basically I'm just going to talk you through this. Which will be in places a little bit unclear without some other explanation, but hopefully you can go back to this and treat it as a wiki type document later. So I'm going to talk about using Gadgetron with Matlab a little more towards the prototype imaging human studies rather than prototypes as you saw from Stan and Olea, more on the side of developing sequences. So we're using Gadgetron on 5 scanners at 2 different centers, and we often have multiple subject fMRI or structural MRI studies that are going on for periods and overlapping with each other. And we want image reconstruction that can be done at the scanner, because it's not really practical usually to store the huge volumes of raw case-based data. And we have various different users using the different scanners. So we need quite a robust way of separating out the different applications. And one technology which is really handy for this is Docker. And that allows both for an orderly operation of different studies, which can be based in different containers. And also the containers provide a reproducible and traceable environment for being able to perform the same investigation repeatedly. And another technology is obviously Git and GitHub server, to allow us to have traceability of different versions of systems. So for today, an overview of what I'm going to talk about is just an idea of the hardware and software components. And there's quite a lot involved in an actual installation with Gadgetron with Matlab at a scanner. I'll go into some details about integrating these different components and specific problems and solutions which we've developed. Then I'm going to use what you've seen today in detail, the Gadgetron Matlab software framework. And in particular, I'm going to illustrate with a case study, which is the one case study I'm very familiar with because it's my work, on reconstruction of real-time 70 segmented accelerated 3D EPI, which is very definitely work in progress. So I've cut and pasted, literally cut and pasted from the development that we're doing. I've left out stuff that hasn't been published yet to some extent. So these are code snippets to hopefully give enough information so that you can see how practically useful the framework with Gadgetron and Matlab is for real acquisitions and real studies with multiple subjects. And then one issue has been that these recons can be quite slow, and Matlab has a reputation for being slow. But I've done a lot of work using the parallel processing toolbox, and I'll show how that can be very nicely integrated with the function composition framework that Christopher showed earlier, and that the other guys were using as well in their application talks. And that's pretty cool. So I'll pause at that point, and if anyone's got any overall questions, or if they can't hear me, am I too loud, too soft, or can't see the screen properly? Can someone say it's okay, because it's deafening silence here?
It's okay.
Thank you, Stan. Okay, so the first topic, hardware and software. So we have 5 scanners, all Siemens, various different software levels and field strengths, and Gadgetron, and Gadgetron Matlab run on all of those. So Gadgetron can compile on the different software frameworks, and the Gadgetron component runs on the Mars or on the Avanto for the earlier VB17 system. It's important to be able to get the data. If we want to do real-time reconstruction, we have to get the data out of the scanner fast enough to keep up with the acquisition. And as a rule of thumb, if you have less than or up to 32 channels, then a 1 gigabit line is a good enough data rate. Going above 32 channels, it's worth figuring out ways to get 10 gigabits. So for example, we have plugged in 10 gig Ethernet cards into the Marses on our Prismas, which have 64 channel head and neck coils. We're quite careful about at least minimizing the invasiveness of connecting up other scanners, other computers to our scanner. So at least at the electrical level, we try to use fiber optics for electrical isolation. That can either be done with fiber optic cards or with media converters that convert from 1 gigabit twisted pair to 1 gigabit over fiber. So that's just for the electrical isolation of the entire scanner system from anything that we might like to plug in computationally to it. And what we plug in are typically, I think like most people using Gadgetron at the moment, we are using separate workstations, although Gadgetron will run on the Mars itself. So I give an example there. One thing I'd like to point out as a hint is that it used to be for Matlab that you should buy Intel, and that is apparently now no longer the case. So Matlab's internal maths libraries now run rather better than they used to on AMD hardware. We typically have one of these workstations per scanner, which is sort of for overall system robustness. If one installation fails, it doesn't bring down operations on the other scanners. And also there's no possibility of competition for computer resources between the scanners. But as you've seen, a Gadgetron server can actually serve multiple clients simultaneously.
I have a question,
the workstation, please.
Are you not talking about
Yep.
any GPU? Do you leverage GPU or only CPU?
That's a good question. So what I'm talking about here is CPU. This is that the AMD Threadripper CPUs are basically now technically, quite superior and faster than their Intel equivalents at a given price. And so if you are buying hardware now for CPU operation, you would probably choose AMD, where previously for Matlab, you would have chosen Intel. For GPUs, I think that the support within Gadgetron is CUDA, so it's NVIDIA tied. Although I suppose there's no problem in an AMD CPU with NVIDIA GPU plugged in as well. Correct me if I'm wrong, David or whoever.
No, that works beautifully. I'm running that exact setup here.
Good. Okay, so we're running Ubuntu long-term support, and Gadgetron works just fine under 18 or 20. Not sure if it still runs under 16 smoothly. I think not. We use Docker, latest version, and then within Docker, we are typically running 1804 because those are the Docker files that are easily available. But I'm fairly sure that that's also been updated to 2004 quite recently, or shortly will be if it hasn't. So one nice thing with Docker is that you can natively expose the NVIDIA GPUs within the container. We're using Gadgetron 4.1. So what you've been seeing with this new external language interface, so fantastically developed by Christopher and David, is Gadgetron 4.0 or 4.1. And what I'll show works on the various versions of Gadgetron Matlab, but I think the latest is 2.0.12. Moment we're using release 2020A, which is the latest fully released version of Matlab. And I'll come to that a bit more with the parallel processing toolbox. And I'll show, as I say, some example reconstruction code. So all of that stuff, and it's a lot of different stuff, has to work together. And I've forgotten a few items for certain. So again, I'll just pause if anyone wants any questions on those. Okay, so then a few little tips of problems with getting all this stuff to work together, and solutions that I and my colleagues have come up with. I think I'm a jack of all trades and a master of none. So sorry, I won't have come up with the best solutions for anything much. But you at least can identify where the weak links might be and where you want to make sure that you've covered those bases if you want to have a prototyping system that can actually be used robustly. So everything we can possibly put is in Git repositories and then somewhere stably like GitHub. So the Matlab source code, the C++ source code from Gadgetron and from libraries, like the ISMRD library, Docker files to create containers, startup scripts for things Docker files can't do, system control unit files for getting systemd to automatically start containers, all of the different XML configurations that occur in multiple places in Gadgetron, little ini files for things that didn't get stuck into XML files. We occasionally have to tune the kernel to make sure it doesn't go off and do lots of paging when we'd rather it did processing. So all of those can be kept track of in a repository or multiple repositories, or repositories containing references to other repositories and so forth. So it can be quite complicated, but it does mean in principle that we can get back to something similar to what we used 6 months ago if we have to acquire more data and a disk has crashed in the meantime, or we've had a scanner upgrade or whatever. Incidentally, that's one nice thing for Gadgetron, that you can get back to the earlier versions even after the manufacturer has upgraded your scanner and maybe changed how their internal reconstructions operate. So, and then I've just shown a snippet here from the beginning of the Docker file that's based on one of the Docker files in the Gadgetron source tree, but we've extended this concept of, let me give an example. Okay, we for example have our own fork of Gadgetron where we've made minor tweaks typically, but we definitely know which branch and which commit on that branch that we are referring to in this container. And for example here, like with what Orléan was talking about, someone was using their container for development that involved BART, so we made certain that that was likewise identified by version. So Gadgetron has very nice integration testing, and perhaps, which I will confess that we haven't made as good use of as we should do. But in principle, with reconstructions, one should have raw data and can supply the correspondingly expected reconstructed images, and an automated test system will rerun Gadgetron when something has changed, which might be our Matlab source code or Gadgetron itself or one of those other underlying libraries, and look to see whether we're still getting, to validate whether we are still getting the same output given the same input. And I'm very slow in ever publishing anything, so I will submit my reconstruction after the peer-reviewed publication. But I've put some snippets on for the technical side today. And obviously the point here is that this is good for everyone. It ensures that bugs haven't been introduced in the underlying things. It ensures that our code is still running when someone else changes some other part of the system. Perhaps David, if you had any comments at this stage about the continuous integration. No, he's probably not listening, that's fine. So all of this, typically, all of this keeping a uniform environment is within the Docker container. But of course, the container has to run on some sort of hardware and operating system. And there we do our best, which is we have a host system, which is also, sorry, 2004 or 1804. We tend to freeze them every few months. We do the security patches and make images, some hopefully sensible IT administration. We then do the integration tests, and if anything's not succeeding, we can just roll back to the previous system. And we have the benefit of having a few scanners with near identical PCs on the different scanners, so we can live test what's wrong, why it's wrong, and it also gives us some redundancy because these Gadgetron installations have to be working, and computers do occasionally fail. So we have a way of swapping between urgently needed systems and less urgently needed. And we rely, as you see up here, we rely on the standard Docker Hub curated Ubuntu images. So I had some questions about Matlab being accessible within the Docker container. So if you want the ELI execute to operate, then the Gadgetron server has to actually be able to locate a Matlab binary to execute in order to execute the connect function in batch mode. So we saw that on the previous talks. And in fact, if you only want to use connect with the debugging, so that wouldn't be appropriate for our neuroscience applications, but would be for developing sequence, then you can use the host networking of Docker, or even outside of host networking if you wanted to, and have MATLAB running outside the container. But in fact, with a little bit of configuration, you can run a MATLAB which is installed on the host, can be run from within the container. So I'll just take you through the tricks here. So there's the use for host networking from a container. So basically Docker wants to isolate out what you're running in the container from the real world, but to some extent we want to subvert that and really allow access to what's necessary from the rest of the world into the container, including MATLAB. Privileged is to do with being allowed to mount within the container. It's not so important here. So we typically have some shared folders for transferring information or data to the container or not, and actually we tend to use this also to share by Samba to the scanner host. We allow the whole of the MATLAB installation tree through into the container. We allow the container to access the X server on the host machine. We allow GPU access, so the container can have access to NVIDIA GPUs. This is now native within Docker since 1900-something. And then the Docker file is an extra capability which seems to be a bug. You're not allowed to specify on the command line. Maybe it's a feature, who knows. So this within the Docker file allows MATLAB access, any process, and in our case, we're interested in MATLAB, access to the GPU acceleration of graphics. I put in some links to these options. MathWorks also actually has a curated container framework to allow you to install MATLAB directly within a Docker file. And they're doing that mainly for allowing cloud deployment of MATLAB. So you could also get MATLAB into your container that way. So then with MATLAB, there are a few, I have a few favorite versions of MATLAB. Basically, most of this is to do with running parallel computation. So using the parallel computer toolbox. So 2017B is great. Anything after that, it turns out to be very slow transferring complex data into parallel computing workers or using the MATLAB Engine API. So beware, either stick with 17B or recently and very usefully for us, from 2020A, parallel pools from the parallel processing toolbox can actually open threads rather than separate MATLAB processes. And critically, that means that transferring large volumes of complex data is much, much faster, like of order 5 times certainly faster than in the previous fastest. And that makes the bottleneck, the data transfer bottleneck that is common for parallel processing, basically overcomes it for the realm of real-time MRI reconstruction with Gadgetron MATLAB. And just for fun, and because they seemed not to put it behind their content restriction wall, I can give you a link to the pre-release notes for 2020B, which has some goodies. And yes, so I've said this already about Docker containers. Okay, so that's the integration of Docker, Gadgetron, Matlab, X Windows, you name it. Any questions about the software integration before I go on to the examples?
With the X integration, can you get plots to show on the reconstruction machine?
Yes, so if you're running, most of those options were nothing to do with Matlab, mostly were to do with X Windows. Sorry, not the first line, but the next few lines. So for example, if you had your Python viewer inside the container and you've done that magic mapping of hosts to container files in that case and display variable, the display should just pop up on the host X server.
All right.
And likewise with Matlab.
Mm.
And Docker's been through a little bit of development of the GPU integration, and it used to be a bit flaky, but now it's pretty much, it just works as you would hope it would work. So the alternative, if it doesn't for some reason, is you're stuck with Connect and running Matlab, as we've seen with people using WSL and things like that, running the Matlab on the host machine versus with Gadgetron in the container. Is that okay?
Yeah, perfect.
So so basically, a year ago now or so, I think, might be two, Christopher gave me a very nice explanation of his function composition programming paradigm, which you have all been blessed with seeing today. And I have tried to follow that method. So what you'll see definitely started out as one of the, I think it's the bucket recon example in Christopher's example folders. We have found it useful to put in an additional plus toolbox, plus utils, or something like that, in addition to the plus steps folder. And we've tried to sort of standardize on having the top level reconstruction and an XML file for Gadgetron at the top level above there. And Christopher nicely gave some more pointers about good structured programming and sharing code. And that's definitely, it would be great that as we develop Gadgetron MATLAB, we're all conscious of this. And when we're submitting our code into the Gadgetron MATLAB repository or repositories, we try and bear in mind, as I say, I'm no expert in anything, so these may not be the best way to structure things in software terms, but at least if we try to make things inter-usable, reusable, that would be great. Yes, one other trick while we're at it is that EPI.xml can very usefully be mapped into the container. So you can edit it from outside, but Gadgetron can make use of it inside. And a little tip if you ever have to do that is you have to restart the container every time you change the too much detail. So with that in, and critically, my PC is warning me that I'm overusing its CPU, which might mean the audio goes bad. Am I still right?
Yeah, it's getting a little bit choppy, Oliver, if you can hear me. I find sometimes Zoom does that. it gives you warnings along those lines. But it's in and out.
Yeah.
You seem okay now.
Okay, just interrupt again. I can hear you fine, and just interrupt if it gets impossible. I'm sorry about that, everyone. Okay, so we're using the Matlab Parallel Computing Toolbox. And so what I'll show is how we have coded using what you've seen today to actually do some real-world segmented 3D accelerated API. So as you all know, Gadgetron can actually be used at the scanner, which is all very well, but if you then send the raw data to Matlab and have to wait 10 minutes for it to be reconstructed when the scan was only 5 minutes, that's not such a big benefit over just doing the reconstruction offline. In fact, you can get Matlab to run quite fast with modern hardware, and fast enough to be appropriate for MRI recons. So I'll walk you through some of the expanded examples starting from Christopher's templates and to show what we've done to try and get Matlab to run in this application. I've literally cut and pasted. I've tried to only edit where there's stuff I really wanted to hide. So there are some occasional comments to show that this really is prototype code. So to start with, we have an XML file. What I want to point out here is so I'm using the accumulate trigger gadget, but I'm not using bucket to bucket, bucket to buffer. The reason is that this is highly accelerated data, and an unfortunate consequence of using the buffer data type is that in this case it will be filled. I think this is 8 times accelerated data, so it will be 8 times larger than it needs to be, and unfortunately that's too big an overhead for getting the data in real time to Matlab. So instead I am transferring buckets, and I think Aurélien also didn't have time to show, but in their talk there is another example of using bucket transfer directly to Matlab. And also, just because it is prototyping, it turned out that some of the flags for the counter for repetitions were not set up in a way that the repetitions trigger dimension would operate. So one of the few bits of C++ I've done is to add this in acquisitions prototyping buffering method, which is a pain in the backside. And I'm sorry to everyone who has to use this, because you have to manually figure out what these numbers should be, and it's different for every single acquisition. But basically, it's a way of blocking, either sending out one large, in this case, larger block of acquisitions as a bucket, and then repeatedly sending, in this case, a smaller block after that. And the intention here is that this is the block of acquisitions that contain the accelerated data reference volume, and these are the multiple accelerated volumes. So it's a way of very inelegantly making fixed length buckets. And as a rule of thumb, if with the current Java accelerated connect code that Christopher has written, if you can block data in some way, either by repetition or in this case by just numbers of acquisitions, to be of order 10 hertz, sending 10 buckets per second being sent to Matlab, then Matlab will be happy and can keep up. Maybe 100 buckets per second you can manage, but not thousands of buckets a second, which would be the case for EPI without this sort of buffering by the accumulate trigger gadget. And then, as you see, we can directly execute, as you've just seen, within the container, and MATLAB's available within the container through exposing the MATLAB source tree. Or for debugging, we use the famous 18,000 connect port, and then that can be connecting through onto the host PC, and we can use MATLAB just as normal on a host. And then, because this is going back to the scanner, we're converting to unsigned shorts using a Gadgetron gadget. So yes, one thing here is the style here is we're doing most of our processing in MATLAB, even when it's might well be possible to mix and match more of the Gadgetron gadgets together with it. Okay, so quick pause.
There's a question for you. Maybe it has been answered. Jack Henson asked, would you please comment on the common hard disk size of a Gadgetron Docker container that includes MKL and CUDA?
From our practical experience, the containers were quite large. And then with a quick comment on the Gadgetron Developers Hangout, which is every Friday at 3 p.m. Central European Time, little advert there. Magically, I think it was Christopher or David, managed to reduce it from 10 gigabytes down to 2.5 gigabytes. Maybe one of them would like to just comment.
I mean, I guess I can comment. It wasn't me. I think it was David. So I think, so we had some really large Docker images. I think that's particularly 1604 images because we had to, Gadgetron moved on to new versions of C++, and we had to recompile large parts of actually Ubuntu. So we had to install a new compiler and recompile Boost, and basically building a system that's more modern than 1604. So those images, like when you build everything bottom up, they can't leverage what's already in the 1604 image, and so they get really large. The newer Ubuntus, we don't have to modify, so they can be smaller. But you still have images that are a couple of gigabytes. Yeah.
I honestly can't remember what we did. Around this time, Ubuntu also made their base images smaller, so that might have helped us quite a bit as well.
So I think the practical size is of order to 2 to 3 gigs now. Okay, we can come back to that in the Q&A session. So I will plod on a little bit, if that's all right. For debugging, in a way, we have our famous Gadgetron listen and then port number and the function handle for the function that should be called when a connection is made by Gadgetron to the MATLAB MLD server. And then just to show a sort of real world recon doing super ghost correction. We have added, or I've tended to use, and this was inherited from the previous version of Gadgetron MATLAB which was an object-oriented thing where G was the name of the gadget object. So G is, I'm here abusing as a global. So it's if you've extracted, so this is looking at the connection header, and I'll show the function below. Some of the XML parameters, you might want them to be used in a number of steps. So for example, when I reconstruct my reference data, I need access to those XML parameters. I can also tag on extra matrices. This is a ghost correction matrix, partly, and tag that onto this G data structure. And I also use it for just little switches like should we use parallel processing within a step. So that's nicely, for example, when I do my first Fourier transform, within this step, I can do it in parallel using the parallel toolbox or not for debugging, for example, to allow easier debugging of the code. So this global, some sort of global that can be passed down to functions seems useful. You can also have other switches that are only have scope within this overall function. So for example, if I want to have my displays appearing on the X server from Matlab while it's running, and then I can just have a conditional. So I'm using this function composition, functional programming style that Christopher introduced. The word next there is like steps in his demo, I think it's, and we can have some conditional formation of the chain of the functional composition. We can also just put some disps in for debugging. This is the 2020A parallel pool threads. It's as easy as that to set up multiple worker MATLABs to be used by the employer MATLAB. And then we're back to where Christopher started today. Connection next. And then I have a chain, as I say, with a little bit of optional formation depending on what we actually want to do. And finally, Gadgetron consume. And that's it. And there's no editing there. That's everything in that recon. So it certainly proves useful, as I was laboring on about having a global structure. And we start this off by sticking the whole of connection header in there. We then parse the XML a little bit. I'm particularly proud of these ones here, which are old MATLAB's way of finally introducing the map object, which allows us to map named objects from the style sheet, conversion from user parameters on the user card. So you saw that last week, and to map those into acquisition time, so useful parameters, or some ones that we've added by editing the style sheet for our own use, KaiPi sampling scheme, for example. Okay, so that's just a function that gives us some globally accessible information. So then the steps functions, so these are the higher order functions that Christopher talked about in the first talk today. So you probably have noticed that they are quite analogous to gadgets in the C++ Gadgetron stream. So they are a way of separating out into a nicely defined chain the different processing steps. we have globals, we have a closure within these step functions. So we can have, for example, this is a step function, reconstruct reference data. We can have some configuration that occurs when the chain is set up. And then we have the nested function. And basically, I keep this convention, the nested function.
Sorry,
same
Oliver, you're
as
chopping up a
the
little bit.
step function.
Can you just repeat that last bit for just about the last 15 seconds, maybe?
15 seconds. So confusingly, and clearly confusingly to Zoom, I'll stop. I'm going to try to not point to things and see if that helps the X server. How is this?
That's better.
It's better, okay. The nested function, which is executed when consume requires execution, has the same name as the step function. You could name this differently. So what I want to draw your attention to here is another choice of data types, which we saw a little bit in Stan's talk, I think it was, I'm using D for data. So basically, this is a structure which can be passed down from one step to the next step, or from the callback functions within the steps, which can have appended to it. So this is a generic structure which can have the different stages of reconstruction appended to it as members of the structure. So this allows for prototyping of rather flexibly passing different data types down the chain of processing. And for example, here in this line, I am doing a first Fourier transform from my utils, my toolbox. I'm passing D and I'm returning D. But actually what's used within the function, which I'll show in a second, is just D dot data here is what's being used internally within the toolbox. And what's being returned is D dot F1D here used after the first Fourier transform. And crucially, I have kept hold of the dot data, should I want to use it, but also the dot header element. So all of this is to enable me later on, when I'm sending images back to the client, to the scanner, or to Gadgetron, and then to the scanner, I need to have the data that are passed down the functional composition to actually include the header from right at the top, although functions intermediately don't actually touch it. So this is just a way of attaching the headers and data to one object. Okay, so we do first Fourier transform, we do 2 more Fourier transforms, and finally get a reference volume in this case. So what's being returned by this internal function is the reference volume. So I want to just contrast that the internal function is returning data. To make sense with what I've just said, this should definitely be D here, but because it is referenced rather than accelerated data is why it doesn't look like this. But generically, this should be a D type thing. That's being returned by the internal function, whereas when the chain is set up, it's only the pointer to the internal function which is being passed through to the chain. Okay, so those are step functions. And then our toolbox functions, utils functions. These are normal first order functions. And the one I just showed was 1D reconstruction, 1D Fourier transform, so a non-uniform Fourier transform. And they can be called directly. We saw parsing the XML, for example, or they can be called from within steps. So I've tried to keep the convention of doing the actual number crunching within these utils. And to stress this, the data structure D for data. So we're passing D, returning D. And this little shim layer in between here is just to really stress the fact that it's being data being passed and then first Fourier transform data that are returned from here. So this was just a wrapper around an existing function. Little tip for the future, 2020B has a built-in function that basically does that very fast. So it does matrix multiplication on the first 2 dimensions of the arguments, vectorized over all subsequent dimensions of the input functions and with appropriate singleton expansion. So it's like the function for unfolding images or applying matrices across multiple voxels within volumes. Okay, we're getting there. Yes, all that fuss about D that I was talking about just now was to allow us finally, when we want to convert into an ISMRM image, in this case, our D has within it D.header, so do the extracting the final header to use it for forming the image header, as well as, in my case, D.vol, so a complex unfolded accelerated data set, which then gets sent as a magnitude image back to Gadgetron. And just as before, we have the step function, and then what gets passed down to the next step is a pointer or lambda function to the internal function, with also the reference to where to get the data from. So that's a very common idiom within the examples, and which we've just followed. Okay, so can I go on for 5 minutes, Valerie?
Yes, go ahead, Oliver.
Okay, so 5 minutes on parallel processing. So Matlab can do parallel processing in various ways, and in particular, when Matlab calls LAPACK, for example, if you're doing SVDs, it will use Matlab's parallel processing. There are various ways to code like binary singleton expansion rather than writing loops to allow Matlab to do things quickly. And there's a sort of trend, finally, after about a decade of people complaining about things being slow, Matlab just put in another random function to make it faster. But Matlab also has the parallel computing toolbox, and finally that has thread pools, so you don't have the huge overhead of copying data between processes, but data can be shared by shared memory between the different threads. Now, Christopher's functional composition paradigm is very elegant from a declarative computational point of view, but it's also very elegant from a parallel processing perspective if only MATLAB could perform the different steps in parallel in separate threads. Now, still MATLAB doesn't. Its main engine, computation engine, operates sequentially. I'm avoiding saying single-threaded. It operates on each operation sequentially. So what I mean by that is it would be nice if while some cores were doing the first Fourier transform, other cores could be doing the second and third Fourier transforms, for example, or unfolding the data at the same time. But as it stands, you won't get that from MATLAB. You get exactly that from Gadgetron in the C++ chain. So I've tried to use the MATLAB Parallel Toolbox to implement that functionality within the multi-step Christopher's framework. So these are just points about parallel processing. Often you have to wait for something in single-threaded mode before you can actually do something useful in multi-core thread mode. And while you're in single-threaded stage, the other cores on your PC are idle and you've wasted your money on your 56-core Threadripper or whatever it is. You might have just got a 6-core one instead. So the solution for Fmri Api, which is the one thing I actually know a little more about, is that you have multiple independent volumes being acquired. So that's begging for some sort of pipeline implementation. So we can say that, for example, one volume is being reconstructed while another one is being acquired. Or we can distribute sequential volumes over different CPUs, cores, up until the point at which we've used all the cores available to us. So I've done this within the plus steps framework, and I basically use par feval, which might not be so familiar as par4, but basically par4 just calls, par4 is a for loop, but then it's repeatedly calling par feval to distribute different iterations of that for loop in parallel across different workers from the employer session. And so I'm proud about this. I'm sure I've reinvented a totally standard idiom. I'd love for someone to nicely explain to me what it is that I've reinvented, because I will learn something. But I found a way to make sure that different steps operated with some sort of FIFO queuing, so that in practice with this application, I can keep 60 or 70% of the CPUs busy while I'm reconstructing, as opposed to avoid a 10% without any parallelization. So that's a sort of 5 or so times speed up of the acceleration. So what's going on here? So this is a step function. So it's our famous external function, which just returns a pointer to an internal function. And the internal function, so basically without parallelization, the internal function would be something like this. It would just call our utility function to do the first Fourier transform, okay? That's commented out. Instead, what we're doing is there's no input being passed as the argument to the internal function. It's actually happening halfway through the function, okay? So we get a volume of data, then we use par feval with our thread pool to ask for the function to be run on one of the workers. And this is MATLAB's not very beautiful syntax for having that done. Julia does this much more beautifully with its thread package, totally analogous. So we submit a job to be executed. This is just boring, but necessary. If this is one of our useful things, the number of repetitions in our API run. So if we've reached the end of the run, we had better wait for all submitted jobs to be finished. And then we use tail recursion, which was the first time I've used this since learning about it 20 or 30 years ago, to do something with the same function. And what it does, and we come back to the beginning of the function now, it looks to see if any of the previous parallel processes have finished, and if so, there's our D, which gets returned. So remember, you have consume somewhere underneath this. So you're repeatedly calling this function. So you're repeatedly calling, do you have any data? I want data. If you do, you can return it, that's great. And then that will get sent back to the Gadgetron. If you don't, you won't return here. Then this is now the consumer for the next step upwards in the chain. So get some, so this is reconstruct one, get some case-based data to work on. And then my little heuristic, which is if you didn't have data available immediately and you've had to go and get some more data, then you better submit that data to be processed in parallel. So this is my way of starting to fill up. If nothing was available, then it's a good idea to start processing something so that it may be available the next time the while true, the consume loop, asks for it. So this does work. It, as I say, uses 60 to 70% of the CPU, which is great. And in practice, reconstructs data that are required with 3 seconds TR in 2 seconds, purely in Matlab, with the assistance of Gadgetron and the fantastic framework that's there. So that's the end of what I want to talk about today. I'd just like to acknowledge Michael Hansen and Suhail Inati for the original version of the Gadgetron Matlab integration, and of course to David and Christopher for basically reworking it into something that actually works for prototyping, even at the level of actual neuroscience studies, and not only as a method for sequence development. I'd also like to please ask if you are enthused by this sort of vision of we can do our reconstruction in Matlab or some other high-level language, together with the lower level language where it's actually the useful thing to do and the appropriate thing to do. The developer hangouts, as I said before, are every Friday, 3 p.m. Central European time, and the guys are fantastic. And the more that you actually are involved, the more this system will develop the way you want it to. I know that from my experience. Thank you for your attention.
Yeah, thanks.